Okay.
Have you ever thought of drawing the lines at an angle? Because the camera is tilted, right? So you get more space, more room on the bottom, actually. I'm not
I
sure.
think Multi has done that before,
Maybe.
by drawing the, like, you know, like.
That work?
Yeah,
Yeah, I think that's
Okay.
spot on. There.
Okay. So what I want to do today is kind of do some stuff that we sort of last time. Did I give everyone the hard copy of the
homework.
homework or did I
Yeah.
thought I did, okay. I thought so, because they had the Christoffel symbols, they're going to calculate them in 2 different ways. One just by brute force and the other doing the derivatives of the basis vectors. So the next homework that you're going to be getting is going to be another one of these calculational things and stuff like this and whatnot. So you're going to be doing a lot of calculational problems and just you have to get used to it. So I want to do a little review, do a little proofs, and then we actually want to finally, at the end of this week, and hopefully before the end of this week, we actually have the Einstein equations. Then we can start solving them. And the first thing we're going to solve is Blackwell stationary.
I won't be here Wednesday.
Oh, I can read it. Okay. So
I just, with my luck, it's gonna be the day that you get some Einstein equations too.
we'll start getting them here today. And I'm going to even quote some stuff in here. I'm going to write them down verbatim so you can see it's just not me making it up. It's going to seem a little. Okay, but it's
You can't read
legit.
a book. You could be just reading, you could be reading out of the
That's
Bible
true.
and just writing random. things.
That's possible, but there's the free version of that, which isn't quite the textbook, it's a little tweaked, but it's basically his first edition of the textbook. And so you actually have that, so you can actually see it from.
He made it up.
Exactly, you just
You-
wrote
you-
the entire textbook.
Okay, perhaps, but Shauna Carroll's pretty good. So with that said, let's just do a little review. So we had this R alpha beta mu nu. So how do we define this?
Partial Christoffel symbol.
Partial Christoffel
Minus
minus partial Christoffel.
double Christoffel,
Gamma
minus that.
gamma.
Put the alpha on the
Alpha.
first Christoffel of each Christoffel.
Alpha.
Anisometric in mu nu.
Okay.
So you go mu nu.
Mu.
Say it right, it's not
Antisymmetric.
anti-symmetric.
Anti, I said anti.
Okay, you said, I
Yeah.
thought you said like my social.
Oh, I see.
I think it's just inside.
Okay, this is gonna be,
Mu nu.
so it's in these two here, mu nu, and then to make it anti-symmetric, this one has to be mu.
Same thing on the other ones.
Mu. And then we know we sum on these, and so we'll have sigmas here.
And let's stick a beta on the
Yeah, then
last.
beta, just beta word less is left. Beta. Okay. Now, if I want to lower this, if I want to make this rho tau beta mu nu, actually, let's do a couple things here. Suppose I want R beta nu. What do we do for R beta nu?
You do a G.
Alpha
No.
equals mu, mu.
Yeah, we sum on these guys here. So this is going to be R alpha beta alpha nu. And so we're summing on these, so there's actually 4 terms here. Okay, and that's going to be this one, what is this one called?
The Riemann curvature.
This is your Riemann curvature tensor, this is
Ricci tensor.
the Ricci tensor. Now, this one is symmetric in,
Beta,
yeah, so this is a second rank symmetric tensor. This is Ricci. This is the second rank symmetric tensor. We're gonna make use of that today. And this one here is your Riemann curvature tensor. This one here, we're gonna lower this. We want R tau beta mu nu. So how do I make R tau beta mu nu?
the G tau on the bottom, alpha on the top.
G.
Alpha on the bottom, tau.
Yeah,
Okay.
yep, you're right.
Where do you want to put them?
Tau alpha on the bottom.
Tau alpha. It should be alpha tau or tau alpha.
Doesn't matter because it's.
That's what should go. This. Now, what do we know of this one? This has a whole bunch of properties to it. What are they?
Oh, that's good.
It is anti-symmetric in mu nu, but also anti-symmetric in
Tau beta.
tau beta. So this would be R, this would be minus R beta tau mu nu, so it's anti-symmetric there. And it's anti-symmetric in these guys, R tau beta mu, this is minus. And then what happens if I take the tau beta and the mu nu and switch them like this?
That's symmetry.
That's symmetric. So this is gonna be R mu nu. Tau beta. This is symmetric in this.
And our homework is proving all of these, right?
Which ones did we prove? We proved certain. I think we proved,
We proved it was anti.
I think we proved this.
I think the first.
I think we did these two.
Does the covariant version of this have a different name?
No, it's just the remind, it just has nice properties.
Okay.
Now, what else did we have?
The derivatives have some property.
Okay, so what was the derivative property? This covariant derivative. Let's call
We said lambda.
it lambda R tau beta mu nu. Plus, now which ones do we rotate? Or cyclically commute?
First three.
Take these first three here and cyclically commute these. So the mu nu is just gonna come along for the ride. And so cyclically commute these, so tell me what you get.
You get beta,
Beta,
then lambda tau.
lambda tau,
mu nu.
you know. And invariably, if you look in books, they do not take this and then cyclically commute them in this order here. This one is often the last. I don't know why that's just dumb.
Does it matter if the way you cyclically permute it, if you went like the other way, it's the same thing?
Yeah.
You don't wanna, so usually if you cyclically commute something, you cyclically commute, you don't anti-cyclically commute. I mean, you can, but normally don't.
Okay,
Those things just always, I don't screw around with, and I favor cyclic. Do it cyclic,
don't make life
you
hard.
just don't, anything with it that can come up with a minus sign, you just don't screw with. Okay. This is now
Tau.
tau,
Beta lambda.
beta lambda, and mu. These all add together to equal zero. Now you're gonna prove this one here. Now, how are you gonna prove it? Because if you're to do this, remember, what is this guy here? First of all, give me the name for this guy. This guy is called the covariant derivative. And it's screwed up. Well, it's not screwed up. What is it?
This is a partial with respect.
Partial lambda. How was next one?
Plus,
Plus
gamma,
gamma.
and it should be times. I don't remember. I don't know.
We have a lambda here. And then you have to have two other variables here. Too. You're
Yeah.
gonna have to have like a sigma and then a delta or something like that.
Wait, so there's no,
So it'd have to be something with two indices.
Yeah, you have this, and then normally it's X add on something here, so you have another thing here, and then you have another, you have like a, what else do you have here?
So is it true that what you'd have there has to be a second rate tensor?
This right here would be a, this is an operator who's gonna act on something.
But what's, oh, I see.
I was, yeah.
So there's nothing that goes there until you.
Right, so this is,
operate
this is
on
gonna,
site.
this is gonna be, right, this is gonna be, here is gonna be acting out like a,
Lambda, no,
I have a lambda, let's.
Oh, it'd be a sigma. delta.
mu,
I have a, I guess
Oh,
it doesn't really matter, psi. Okay, so then you have a psi, and then you have a,
psi also, no?
Psi would be with it.
you'd have, then you have to, you'd be something on the delta. here.
Delta.
What am I missing here? I think there's usually a delta type thing here, but there isn't.
Yeah,
I'm missing something here.
yeah, there's a delta. Oh,
I'm missing something. Here.
No, I don't think so. That's what I have.
Yeah, that was three. There must be something else in here. Oh, it doesn't, it's not, okay, I've been up since one, so you're gonna have to really work. There's something else here that's gonna have the signal in here. Now, it doesn't, okay,
it looks like you multiply everything by a basis vector that has the sigma on it.
You can, but not, that's when you have this being the vector here, when it's not the vector here, it doesn't have it. It'll come back to me.
So that's how we wrote it, like how the alpha.
That's when we did this stuff here. We did that,
I see.
okay, and this is the component. It'll come back to me at some. I just have to- So there's something else here now. This would be a real, if I use it in this form here, and then use this form here, this is gonna be a first class thing to do the proof. What do you do?
You say that something's true, so all the terms, a bunch of terms go to zero.
You go to certain coordinates,
Geodesics.
geodesics, and the geodesic coordinates, what do we know?
That the
The Christoffel symbols
partial-
equal 0.
partial.
All the partial of your gammas are,
Partial of G is zero?
okay, these are
Zero.
not equal to 0,
I don't-
And the gamma.
but the gammas
is
are
equal to 0.
0.
Yeah,
So what happens with this term here?
That's a really weird definition, but I mean, that makes sense, but we defined it as a partial of the space chart metric.
I mean, okay, this is the upshot of what we had here.
Yeah.
Is that basically we're going to the locally flat space, and so this partial G here, the mu nu here. Or let's say a sigma here like that. These are gonna be 0. The implication here is that this is. a
Yeah,
0
that makes
here,
sense.
But this is not the 0 here. This is locally flat. Okay, now what's nice about this? Because it kills this term here, so we don't even have to worry about this. And then what happens with these two terms here? They go out as well. And if you remember, we actually worked this out. So when you actually do those proofs, remember, have that big, long, messy thing. You can actually use that in the proofs here without going through that whole stuff.
So start from close to the.
Now, what I would do is if you're don't feel comfortable getting that one result, I'd probably go through and do it just to make certain you feel comfortable with it. Okay,
I think I know how to correct it.
tell me.
So your sigma has to be psi
Oh,
or something like that.
Yeah,
No,
this
this
is
is just for covariant, maybe.
yeah, thank you. Okay, I had a sigma, size, these would have to be the same. This is all fine. Which is why there was no other term. I couldn't think of what it was, but as I said, I've been up since 1. So my brain is not working. Thank you.
I think that's good.
Okay, so, any questions to that? So you're gonna go through and do this, and again, only you. If you want to show that you're brave and you don't worry about danger, you can go and actually do it in this full form here, along with that full form here, and have fun with that. I won't give you any more extra credit for it, and it's something I wouldn't even bother to grade it, because basically it's gonna hurt to grade. So if you do it in terms of geodesic coordinates, so that this reduces to here, and then these guys go out, and then we had to work out those here, it's gonna actually be fairly simple to do.
Do we get bravery points?
Yes, you would. I'd give you a very point.
Pity points as well.
So, okay, this is, I think, should I tell you about homo and vir? In Latin, there are 2 words for man, okay? Homo and vir, okay? This is more homo, like in homo sapien. It's more kind of generic man. It's almost more of like a cultivated man. So this is kind of more, I don't know, gentleman or something like this. Vir, we get virile from it, and that actually means manly. And so there's this big tome of some esoteric philosophy that existed. I can't remember what it was. But Cicero, who you read a lot of his letters if you take Latin, actually wrote there's a lot of correspondence between him and his brother. And so Cicero was talking to his brother and says, if you can go through this whole tome, I'll consider you vir, meaning manly, because you got through this thing. But I'll consider you homo, meaning cultivated. Okay, I thought that was fun.
Nice.
They had fun. Yeah. He's razzing his brother.
Shaming based on whether you can read a book of philosophy.
I guess it was just preposterously long-winded and just extremely long tome on with a lot.
Honestly,
Nice.
that was in this.
Okay, so
Full of wisdom.
that's what we did last time. Now I want to do one other thing. And I shouldn't put it. So let's go through and write and what do we call that theorem? That theorem is called the identity.
No idea.
Bianchi identity. Okay, so let's go through and write it again. And so let's do rho. This is R. alpha beta mu nu. I'm just rewriting this again. And this is gonna be rho beta r. That new, I'm gonna, oh. I want something I'm not gonna confuse. I'm gonna say tau. That doesn't look like anything else. So this will be beta, tau alpha, mu nu. And then we're gonna have beta, alpha, r, beta. Know that equals 0. Okay. I'm gonna take this whole thing here. Don't write this down yet. I'm gonna multiply this by G. Beta mu. I reserve the right to make this a daily homework at any moment, just so you know. Okay. G. Alpha mu. How could that possibly be wrong? Okay. So let's go through and work out each of these, what this is gonna be. What would this term here become?
Have we write this yet?
Yes, we're gonna try. If it doesn't work, it's gonna become a daily homework. Okay. So let's look at this one. What is this term here gonna become?
Which one? Sorry.
Let's look at this guy.
That's the, you want like the actual expansion?
Well, if I do that,
Oh,
so here's the Bianchi theorems. I'm just randomly multiplying by this guy here for no good reason.
So
So
the first thing we're gonna have, the,
beta and mu would be.
Okay, this alpha will go up to the top. And that'll become alpha nu.
So the beta.
What is this beta gonna do?
Also gonna go up.
Go up to the top.
would become a mu.
Tau will stay in the
And then this
first
is gonna become, this is gonna become mu.
Tau, mu.
Tau, mu, nu. This cell equals 0.
Wait, but the mu would become alpha up at the top, right?
Is this alpha here because of this guy here? It's gonna become-
Oh, it only changes.
And what is this guy here?
Oh, tau mu.
R tau mu. Okay. Now what about this guy here? Okay. If I'm gonna take this guy here and I'm gonna switch these two here. Right, so this is antisymmetric here. Okay. And so I switch it with this minus sign here. Now what is gonna happen? What is this guy gonna do to the alpha?
It's gonna raise it and make it become a nu.
And that's gonna raise and make a new, so I'm gonna go like this. Is that okay?
Mhm.
And I still have this guy here. Mhm. Now let's do this guy here. This guy here
Gonna become a mu.
is gonna become a mu. And this guy here,
Alpha becomes a mu.
I'm going to switch these two here.
Should they all become?
No, I'm switching things first. I'm gonna switch these two guys, and I'm gonna switch to these two guys here, which keep everything the same. Right? So this will become R alpha tau nu mu. Right? Because I've switched these, so like
Multiplied by a g.
here, then I switch these two here. Okay? Now now this guy gets multiplied by this guy,
Alpha nu.
so that means if this goes up here, it becomes a nu. I think this is actually correct. So what does this guy become?
R tau mu.
R tau mu. Now, what is this guy here?
Negative delta t. The beta mu.
Beta mu. And this is also multiplied by G beta mu. What does this do here?
Oh, that makes the scalar.
Yeah, this goes to here,
Mu, mu.
and this is just R. And then these two, are these the same term?
Yes, they are.
Yes, they are, because the mu, the new would be called
mu.
dummy variables. So this is 2. And this guy here. Was 0, so this tells them that this guy here is equal to 1/2. Here. Now you can look at that and say, well, thank you, that's helpful. Turns out it is. Okay, does that make sense?
Now,
Okay, tell me when you got that copied.
You might have to keep going without him there.
Okay, to be honest, this one takes a little practice to do. The only way to, I always look at the last term here, and I know the last term here should become, what it should become, and then I have to back calculate to figure out what I need to get it.
But this in itself is a proof.
What?
This is a proof.
This is the proof for this result here. And there's a reason we want it. Can't wait to find out what it is. Take good notes.
try. So potentially left the first term with a contrarian derivative or covariant, sorry.
One is up, one is lower.
Is this kind of names?
No, this is just a thing. Okay. This is called something you shouldn't be proving that when you've only, since you've been up since you're in the morning. But anyways.
You got it.
Okay, got it. Yeah, okay.
Yeah, they do.
Let me know when you have that done.
What does that mean?
Well, in conjunction with something that's gonna be important.
So we connected
The
the,
1/2 just makes me think.
No,
connected the Ricci tensor with the, what's the R scalar called? The curvature scalar?
this is called your curvature scale. Yeah. Now,
We're taking a derivative of a scalar? That should be just,
Scalar doesn't mean constant.
yeah, but
Okay.
that should just be
Now.
a partial.
Like I'm saying the Christoffel.
let's ask what is, so let's define. The Einstein tensor. G mu nu as. We've had this before. Define it to be R mu nu minus 1/2 G mu nu times R. That's how we define the Einstein tensor. Yep. Oh, we would like that 1/2. Now let's ask, what is? What is that?
I think you might derivatives.
Oh, contravariant.
Well, let's just take it. So if I have this guy,
Is it the partial?
let's just go through and put it in here. Just see. And we're not gonna overthink it. That's gonna be this guy. Minus 1/2. Now what happens when this? X on here and Y. You have
When it
a,
acts on what? Which
when
one?
this from here, X on here, get this. When this X on here, you'd have a product rule. Well, what do we know about the G's? These G's have metric compatibility, meaning
They equal 0, the dot of them. is zero.
when you take the derivatives of these, you get 0.
Mhm.
Okay,
So you only get one term.
so this is really 1/2 G mu nu. gamma, del nu R. Do we know anything about this guy here?
Maybe if we follow the arrow.
So this goes to what? This goes to 1/2. Gamma mu R minus. Hey, what would happen here? G mu nu
Yeah.
del nu.
Same thing, 0.
That's gonna lower this to be 1/2. Here. This is 0. Woohoo. Okay, so what do we know about this G mu nu? This G mu nu is a second rank tensor. Is it symmetric?
Yes.
So G mu nu is a second rank tensor under a generalized coordinate transformation. Is a second rank symmetric tensor.
Dr. Love,
Yep.
is there a particular reason why you put the del operator in between the G and the R?
Yeah, because when this acts on here, you get a product rule.
Oh,
Okay. But when this
Got it.
acts just on this, you get 0 because of
Gets
metric
it.
compatibility. Okay.
And that assumption is just our attempt to make everything prettier. The
Correct.
metric
I mean, people do actually do these calculations where you don't have that. And then
Do they?
I would argue this is physics when you stop doing the physics. I would say no. Okay, that's no.
So the metric compatibility parameter seems to be represented in the true physics.
It does. Yep.
And any like advancement towards why that happens?
Well, I know it really makes life nice for calculation wise.
But it just does recreate the.
I mean,
physics.
it gives rise to nice properties to the covariant derivative that we like. Now you could say, well, maybe that covariant derivative doesn't have those nice properties. And that's perfectly fine. You can do that.
But in life, it seems to be having those properties.
Correct.
So
I mean, ultimately, science is experimentally based. I mean, so.
got it.
So a symmetric tensor, and obeys this.
That kind of seems like also metric compatibility, something.
Well, it isn't, but it's gonna
But
be
it's just a
really,
capital
it's
G.
gonna be connected with conservation of energy. Initially, Einstein just said this guy. Then he realized-
Energy is a constant.
No. You're gonna see why we need that.
wait, so how did the G mu nu go away in this?
Which part? This G mu nu, I use this to lower this index here to a mu.
Oh, and so,
There, we now have all the pieces that we can actually now give a this is not a proof to do. Okay, this is gonna be a plausibility argument for the Einstein equations. Finally, okay, so. Plausibility. For the Einstein equations. And I'll give you the equations again. This is going to be G mu nu equals 8 pi G c to the 4th. G mu nu. So that's what we want to get.
And this capital G is the gravitational constant.
Yes, this is the 6.67 times 7 minus 1. Okay, and then once we get this version here, C is going to be 1. Okay, once we get past this point here, I just want to show you, I want you to see what C to the 4th. And people could say, well, you could just do dimensional analysis. Yeah, but I don't want to. Once we get that part, then C is equal to 1. We're funding free, I tell you. Okay, and this is, I'm gonna put this in here. So this is actually right from an expert, well, he's actually a program physicist. He actually and evidently has a reputation for being a very good teacher. So he calls this right here, he's gonna, so we're gonna use the minimal coupling principle. Okay, and this is what it is, part one. I'm gonna give you exactly, I'm gonna write it here. You're gonna take a law of physics. Valid in inertial coordinates. Okay. In flat space time. Two. Write it, referring actually to this part of the equation. Write in a coordinate invariant. This just means sensorial. In other words, in terms of the, the mu nu type stuff.
What
Right,
are inertial coordinates?
it's gonna be basically just the same coordinates you have in classical mechanics.
Anything that moves, like,
Well, not accelerated, or anything. Well, it could be accelerated, but normally it's gonna be like just a stationary frame.
okay.
Right, in coordinate invariant sensorial. form. In other words, something where you have like what the alpha and beta values are, something like this. You're gonna have indices. Okay. 3, assert. Okay, this is not a proof. This is a plausibility argument. Okay. Assert that the resulting law remains true in curve space time. There. And then he gives it another, I'll give you the next part. It's going to be called the comma goes to semicolon rule as a joke, but we'll get through it. We'll see that. So we'll get another name. Okay. So this is going to be the principle. So let's actually go through and do this. And what we're going to do is we basically want what's called Poisson's equation for gravitation. So let's put this in here. So apply this approach. Apply these rules to Poisson's equation. Gravitation.
You know anything about this guy? Or some?
Well,
You know anything about this guy?
the name means fish.
Nice.
So and fish is good. So he must be good.
Okay,
Okay.
it's the only thing I heard is was it the coefficient?
The Poisson ratio.
Yeah.
Okay. He's actually very important in electromagnetism. So let's do a little bit of electromagnetism, then I'm going to show you how it goes right over to gravitation. So recall from electrostatics.
Dr. Lenz,
Yep.
is the inertial coordinates in flat space-time, are they 3 dimensions or do they also include time?
We'll have time in there because we're going to be taking time derivatives. But and you're in flat space-time, so you'd have all the standard 4 coordinates
Okay.
here. But it's not going to be in the case we're going to be using it for. We're not going to have to worry about that stuff. You'll see why.
Okay,
Okay. Recall from electrostatics. 1. Okay, so from 125, what's the electric field? It's equal to minus your gradient of your potential. Okay,
That potential is phi now?
phi. Yep. Okay.
Is it because it's like that A plus something?
Well, you could, this would be the whole thing if you had electrodynamics, but electrostatics, you don't have this piece here because it's static.
Mhm. Okay.
So this is the care. Okay, and two, Gauss's law. In differential form. What is Gauss's law in differential form?
It's the divergence of E
The divergence of V equals,
minus the change of B with respect to time. No? Oh, no, that's the. that's the
Row
law.
of Epsilon.
Row of
Oh,
Epsilon.
no.
Let's take this and put it in here. What is a divergence of a gradient operator?
Zero? No? I don't know.
So this is gonna be,
Oh, the second. derivative.
dotted into minus I hat, partial phi with respect to x. It's a hat partial phi with respect to y. It's a hat partial phi with respect to z.
So just
What is that?
minus Laplacian?
Exactly. That becomes your function. Remove this.
I've never asked you, is a Laplacian the same as taking the gradient 2 times?
No, because the gradient is actually a vector quantity.
Yeah.
And this is a scalar quantity.
Okay,
If you did that, you'd then have cross terms. It'd
Okay.
be really, really screwed up property.
got it.
So this is just gonna be this. This right here, this is Poisson's equation. For electrostatics. Actually, to solve it, you end up with something referred to as a Green's function. When you get a Green's function, that's when you start becoming a big boy in physics. When you have a Green's function, that's when you start becoming an adult.
Scary.
One of those things you look at and go, oh no, it's a Green's function. It actually has a nice implication. Okay, what I'm gonna argue is that that when you go over to basically apply this to gravitation, in gravitation, you get the exact same thing. This just gets tinkered with. So we'll see. That when that we'll see that in gravitation, in Newtonian gravitation. We end up with this. This is your gravitational potential. This is going to be 4 pi g rho.
So, and the rho is the mass density?
This is your mass density here. Okay. So let me just kind of show you where this is. So this is actually the grand form of writing Newton's law of gravitation is actually this. So in that first, let me just kind of outline how this is going to go here. So it said, remember how the prescription went for minimum coupling. Take a law of physics, Bell, an inertial frame in flat space time. Hey, like this. Okay. And now what does it say?
Oh, you haven't shown it us?
Well, I want to show you kind of how the argument's going to go.
Oh,
And then I'm going to prove it.
Got it.
Okay, then write it in a coordinate invariant tensorial form. So look over here and say, I don't know what this is. But I know that this right here is a mass density. And what kind of quantity does that relate to that we've had?
J?
No,
Oh, T mu.
the T mu nu. Okay, so this is going to be related to. This is related to T00. So what is a T00 component?
That's your density.
It's your energy density. And so this is gonna be really kind of, it's gonna have a C squared in there. Right, because you'd have your, right, so this right here would be your MC squared over your volume. This right here would be rho, would be like a rho C squared,
Mhm.
like that.
Oh, right. Yeah.
Okay, but that's related to T00. Okay, now tell me about T00. T00 is the element of a, what kind of rank tensor? Second rank tensor, and T mu nu is also
Second.
symmetric.
Oh.
So what does that mean here? What that means here is that this side here had better be also a
Symmetric.
symmetric second rank tensor. Okay, we have two choices for this. Okay, well, I'll make it more rigorous than this. What do you think those choices are? R, so this could scale somehow as R00 with some weird factors, who knows what. Or, now we have another one. Or G00. Okay. Now so we have that there, and then what's the next part? It says, now assert that the resulting law remains valid and occurs spatially. So then what are we gonna say? We're gonna say, well, this guy here, let's take all the constants, have no clue what to do with them. Let's put them in a constant. Sean calls it kappa. Look, I know the guy. Okay, Carol calls it kappa. And since I learned from Carol's book, I'm gonna call it kappa because that's what I call it from. This right here in general is gonna be what? T mu nu. And so then what does this have to be here? Then this has to be R mu nu or G mu. Has to be one of the two. From this idea here. Now I'll make it more obvious about why this is gonna be this. Right now, I want you to see the overall philosophy we're using. Now, initially Einstein had this, and I think Hilbert, had this one here. Then this is where Einstein came through as a physicist, he knew something more. He knew another property of this guy here. What's another property of that guy here? And you had it on the first test.
I just have a question.
Yep.
So, because that side is related to T00, you're saying to keep the equation,
Then they were saying whatever this side is, we know since this is a second rank symmetric tensor. Whatever side, this has to be a second rank symmetric tensor.
to keep them equal.
And so we have two choices here that we have. Now, what is this one here? Remember that we actually showed that basically this guy here is equal to 0.
Oh, yes.
And if you write it in the more grand form, it's really this. Okay. Now, hey, what's the problem? Why can't we have this?
That's not.
Yeah, we know that when we do this here, it's actually equal to that, the operator, the covariant derivative of your scalar tensor, of that 1/2 and stuff like that. So what are you forced to do? You're forced to go to this guy here.
And that's the continuity equation, right?
Yeah.
Exactly, yeah. Okay, and so that's why we're gonna go with this form here, because basically this term here does not satisfy this. Now, let me just, I'll basically give away part of the plot here. Okay, so this is why we're gonna go with the G mu nu. Okay, now somebody could say, not quite. Okay, there is something else we could have. Someone else could say, I could have G mu nu. And I could add, maybe I'm just going to take a constant, for no good reason, I'm going to call this capital lambda. And then say, I'm going to have a G mu nu here with this. Because this is a second rank symmetric tensor.
Yeah.
Does this still satisfy it?
Yeah.
Because of metric compatibility. So somebody could say, oh, I can have this just as well. Okay. And this becomes,
Oh, the Einstein equation.
well, this right here is going to become the Einstein.
Does not become.
It's a constant, and it's going to apply to the entire cosmos.
Cosmological.
That'll become the famous cosmological constant. Okay.
Which
is
is actually constant, is it?
No, well, actually, people don't really, no one has any clue.
Oh, wait, no. I think
Okay.
the latest thing said it was essentially 1. It was roughly 1.
Depends on what units you're using.
As you added all the different components up of the different.
Oh,
things.
that's omega. That's
I
omega.
thought it related to that though.
It is. It's gonna come into that term. but this is just the cosmological constant. So you could actually have this, and the reason why is that, if you have this guy, initially, people thought that the universe is basically static and not moving. And then Hubble came along and realized that everything was basically moving apart. And so to fix it, Einstein threw in this term here. And then it turns out that Lemaitre showed that actually, if you just have this, you get an expanding universe anyways. And so you didn't need this term, and so that became Einstein's greatest mistake. Until it wasn't, when it turned out it's actually been measured and acts like a repulsive vector. And you could say, well, what on earth is this term? And that's a great question.
That's what we call it, isn't it?
That'd be the dark energy. Now, whether they're the same, people debate this, but this would be the cosmological constant. Many people would say it's the same thing as dark energy, and it's going to act like a repulsive gravity. But in principle, you could have this here. But notice you're just putting it in by hand. Because again, this isn't rigorous what we're doing here. It's a plausibility item. Okay,
We're trying to guess what it actually is.
Yep.
Kind of.
by doing this part here. Now, let me just say a little bit more about this. So when is this going to be valid here? This right here is going to be valid when we have a weak gravitational field. Okay.
What is, sorry?
This right here, this equation here is going to be true, valid for a weak gravitational field. And it's also going to be basically, it's non-relativistic, not relativistic at all. And also, there's no time dependence in the gravity. So with this expression,
What's the name of that Greek letter that you put in front of the
the
letter?
capital lambda. So, the Poisson. Is, valid. For weak gravitational winds. Let's say 4 alpha 1. Weak gravitational winds.
And it's written as G mu nu equals K T mu nu,
Which part over here?
in the tensor form or tensorial form, it's written as G mu nu equals K T mu nu.
Correct. What have we done with it?
How could
It's
you
gonna be either
mistake?
this or this, and it's gonna have to be this one here, so we're gonna have to say the G mu nu. Is gonna equal this kappa, T mu nu. When we work out the kappa here, this kappa is gonna be the 8 pi G over C to the 4th.
Great, thank
Is
you.
what we're gonna see. So weak gravitational field. It's non-relativistic. Meaning that any velocity is going to be much less than the speed of light. Okay. And it's also static. So phi does not depend on two. Okay, so I think I'll call it quits with this. So what I'm gonna do next time I'm gonna show you why we get this. It's actually, it's not very easy. It's not that hard to do. We'll get this, and then what we're gonna do is, we're gonna kind of go here and figure out what this is gonna have to mean. And then we're gonna take the, gonna look at the geodesic equation, put in these limits here, and then from that, we can figure out how this R is gonna have to serve. But don't confuse what I'm doing with a proof, because it's not a proof. It's a plausibility.
Are
Which
we
seems
going to be
interesting.
doing a rigorous proof of it?
There is no rigorous proof of general relativity. There's no rigorous proof.
Oh,
But it works.
so all of general relativity relies on the plausibility argument, essentially, but we
Yeah.
see that it works, so we're like,
Now, what you can do, you can also, okay, private conversation with these people. You can also do a Hamilton's principle. Remember how we had Hamilton's principle where your action is this? And then you can minimize this to 0 and got Lagrange's equations. Okay. Well, you can do the same thing here. You can say, well, what I can do is I can write a Lagrangian for this. And what do? You basically guess the thing. It ends up being this, basically the square root of the determinant of your G matrix. Well, that's obvious. Okay, times your scalar function. Well, that makes sense too. You know, how could it not be there? When you go through a calculation, which is involved here, you get the Einstein equation to say, oh, see, this is, I've rigorously derived it, and you have it. You basically, you made this
Guessed
form
it, but
here,
then the rest.
and then it gives basically the other equation. And so that's another way to do it. We're not gonna do this one, because you end up getting, you get this weird term that you don't know what it is, and say, oh, well, it must be the following. Really, because you get this awful looking thing, you say, well, that has to be T new. That follows,
So what is static?
there's no time dependence.
Okay.
So if we take the time derivative. Of 5, we're gonna get 0. And everything then will fall out more. If you agree with the assumptions we made, everything will then fall out more or less rigorously. You could say, well, I don't agree with the assumptions, well, that's fine. But this is what we're gonna do. But it's not a proof. You can't prove these Einstein equations.
So we're gonna use these 3 tenets to then backtrack and go and actually get the Einstein equations. But the Einstein equations will be general.
So what we're gonna
Because it's,
we're gonna find out that this can basically be written as this. Okay, with weird things here.
Mhm.
And we can't have this because of this guy, so we have that. And then we're gonna go through and solve it for the capital.
but
I mean, it's really good.
in the Einstein equations, you can have relativistic
Correct.
movement. This is saying it's not.
No, this is saying the Poisson equation. In other words, this equation right here, only this equation. Only that equation is valid in these, and this is reverse, this is true. Okay, so what we're gonna say is that when we have the Einstein equations, if you look at this limit here, you better get this,
Okay,
okay? And so this is why, so we're gonna say that once we have this, we know that this has to be related to T00. So we're gonna kind of backtrack by using that minimal coupling thing. Then we start off with the law of physics, look at some inertial frame. Do the other little jazzy stuff there, and then they're gonna pop out. It's a plausibility. It's not a proof at all. And you can't prove this. That makes sense?
So with the whole not letting, it must be equal to G because of the continuity equation. Can't you still sort of argue it still could be equal to R and then,
You can, because again, if these two are equal, then any property of this has to be the same as the property of this.
okay,
So if you would take,
Okay,
if you would take
because
this
you're
on both
gonna-
sides, this will be equal to 0, and this will not be 0.
because you're
So you can
really
have
just subbing in for that
Correct.
equation. You're
Yeah.
not sort of building. Okay, I see. Thank you.
Then once we get that, get this, then the first thing we're gonna look at then is non-rotating black hole, Schwarzschild solution.